So this is the diagram of a diopside anorthite eutectic system, and this is a eutectic point. Say I is the eutectic point, and you can see the starting of melting temperature of pure diopside is this, somewhat below 1400 degrees Celsius, whereas the starting of pure anorthite melting temperature is at say 1550 degrees Celsius, like that. Whereas if we have a mixed composition of say X, then we can get melting point from the range from here to here, whereas for diopside is here to here. Remember, at the eutectic point, both the crystal will form because it is at the midpoint, it is at the intersection where we will see crystallization of both diopside and anorthite. So let's start how this will work. Okay, so let's say this is the first scenario where we are taking a bulk composition on the right hand side of the diagram. Okay, the right hand side of the diagram, that means on the liquidus of the anorthite field. Okay, liquidus of the anorthite field, above the liquidus we are taking a bulk composition. So anorthite is greater than diopside here at composition A is a bulk composition of say diopside 20 and anorthite 80. Diopside 20 anorthite 80, which is plagioclase rich. Okay, it will be plagioclase rich, the bulk composition of the melt. Now for temperature corresponding to A and bulk composition X bulk, we taking it X bulk of anorthite 80 and diopside 20 here at A. So we have only one liquid phase here, so it is a liquid phase. This is the liquid phase. So phase will be 1. There is 2 component. So component again 2. 2 minus 1 plus 1 equals to 2. So both T, X are variable. Both T and X are variable. Okay. Remember. Uh, okay. Anyways. So we have 2 components and 1. Here the formula changes to 1. Okay. Remember, this is 1. Formula for eutectic will be F equals to C minus P plus 1. Remember, okay? C minus P plus 1. So 2. So both T and X are variable in this phase. Now at point B, F equals to 1. At point B here, when it touches the liquidus curve, F equals to 1. Because at any line we get a degree of freedom 1, whereas in any field we get a degree of freedom 2. Remember, in a solid solution phase we are using or say in the water phase we are using F equals to C minus P plus 2, whereas in the eutectic we are using F equals to C minus P plus 1. So this is very important, often students mistake in this, so remember this. Okay, so when it touches the B, the first liquid will form, which will be of C composition, that is pure anorthite will start crystallizing out from the melt. First crystal that will form will be of anorthite composition, pure anorthite composition. In this eutectic system, no since solid solution you will be getting a mixture of crystals, right? Say albite and anorthite, you will get a mixture of albite and anorthite, or olivine, you will get a mixture of phosphorite and phyolite. But here, whenever the crystallization is happening, it will form pure anorthite here, and see in this point, like this, as it progresses towards the eutectic. So in any bulk composition, after hitting the liquidus, it will follow this curve, and the last crystal that will form will be of eutectic composition. Even if you take it here, the last crystal that will form will be of eutectic composition, whereas the other crystal that will form will be of either pure anorthite if it touches this curve, or it will be of pure diopside if it touches this curve. So F equals to 1 at B, first crystal of pure anorthite appears as liquid starts cooling. Okay, line intersects at C. So it is intersects at C, and this is the first crystal that will form. Then a continuous reaction, which is liquid 1 giving anorthite and liquid 2. Okay, liquid 1 giving anorthite plus liquid 2. Next is liquid 2 is more diopside rich than liquid 1. So as you can remember, this one is anorthite 80 and diopside 20, but it is giving crystal which is of pure anorthite composition. So as T decreases, more and more anorthite crystals and solid and total solid composition follows path CFH. So the solid composition will follow the path CFH, whereas the melt composition will follow the path ABDI. Okay, this is the path followed by the melt, whereas this is the path followed by the crystals CFH. Then it will come to G, and then it will come to J. So as T crystal, it will follow CFH and liquid evolves along BDI, along BDI. Okay. And the discontinuous reaction, the reaction at point I, remember the reaction at point I will be a eutectic point here. So at point I, the diopside starts crystallizing along with anorthite. So at point I, the first crystal of diopside will form along with anorthite. So here both the crystal will start forming. So as the melt progresses from B to D, you will notice that it is constantly giving anorthite crystal. So anorthite elements will be depleted in the melt as it slowly progresses from B to D. So at point I, the diopside crystal crystallizing along with anorthite. So liquid will give anorthite plus diopside. So liquid will give anorthite plus diopside, and no other liquid will form. No liquid 2 will form here at eutectic point. It will only give two component, that is anorthite and diopside. So total solid composition follows GH path. It will follow GH path. At point I, f equals to 0, system has no independent variables that can change the system, and the system is stuck at invariant point, that is I. After liquid is consumed, phi equals to 2, f equals to 1. Now temperature can cool down the solid line along G and J line. So along the G and J line, remember along the initial bulk composition, it will follow till the end, till it hits this point, or even below, up till it cools. Okay, so it will follow the inside the uh, below the solidus, inside the solid phase, it will follow the GJ line after passing through the eutectic point. So it will come here and then it will follow. So at this point, remember, up till I, before hitting I, it will constantly give anorthite. After hitting I, it will give both anorthite as well as diopside, and then it will follow this line GJ after being totally solid, and no melt will be involved after this line. So resulting rock texture will be a dominant mineral anorthite forming laths or tubular grains. So it will form anorthite laths or plagioclase or feldspar laths or tubular grains. Lath means a rectangular shape type of thing, rectangular type of a, or a cuboid type of a shape it will form. Texture are intergranular or ophitic, subophitic with diopside surrounding plagioclase. Okay, will form. Let me draw it to you how these textures are nothing but it are the how the it is actually shows the arrangement of minerals in a rock. Texture is actually the arrangement of minerals in a rock, and it can help to identify different rock or different conditions in which it has formed. Okay, textures are very important. We will come to textures in maybe in the next lecture. So it will be very interesting. So for now, I'll just show it to you how these textures look like. So say intergranular texture will look like this actually. So let's say this is actually the microscopic view. Okay, this microscopic view where we study the different textures. So intergranular texture will be, say, these are the laths that will form. Okay, and in between you will find some, in the interstitial spaces you will find some diopside forming pyroxene crystals. So these are anorthite, these are diopside, and this is intergranular texture. Okay, these are intergranular texture. In cross polars, you will sometimes find this twinning in these rocks, twinning, and the cleavage direction will always be parallel to the elongation direction. Twinning will be always be parallel to the elongation direction. So twinning you will see in crossed polarized light. If you have followed our optical mineralogy class, then you will know what twinning is, right? Like this. This is what intergranular texture will look like, where large grains of anorthite will form as lathe shaped, and the interstitial spaces, that means the void spaces, will be followed by crystallization of diopside. So a rock texture where smaller mineral grains fill the spaces between larger mineral grains is called a intergranular texture. And next is ophitic texture. Ophitic texture is when a lathe-shaped plagioclase is enclosed within a mineral. Say it can be olivine or it can be pyroxene. So I'll just split it into half to show you to how ophitic and how subophitic texture looks like. So an ophitic texture will looks like this. Ophitic is this ophitic, and this is subophitic. The ophitic texture will looks like, say this is a pyroxene grain or it can be olivine grain, where you will find this is a plain cross polarized light. Okay, so you will find enclosed are some of the plagioclase laths. This is pyroxene or it can be olivine. In this case, in the eutectic system that we have studied, so it will be a pyroxene diopside. Here it will be anorthite or a plagioclase or a feldspar. Okay, and subophitic means the same thing, but it will be partially enclosed. It will be partially enclosed. Laths can be small shape or shape too. So this is pyroxene, this is anorthite. Okay, so this is our aphatic texture where it is partially closed, partially engulfed by the pyroxene or the olivine crystal, and where here it can be it is totally enclosed by a pyroxene olivine crystal is called a subaphatic or a subaphatic here, and it's a aphatic texture. So here in the eutectic you will consider the host mineral as a pyroxene or diopside, but aphatic texture are shown by olivine also, which engulfs the plagioclase. So this is example of aphatic, subaphatic, and intergranular texture. So the intergranular aphatic texture you know now, with diopside surrounding the plagioclase. Remember, diopside surrounding the plagioclase. So now overall rock type will be gabbroic or anorthositic texture depending on the cooling. So depending on cooling, the overall rock texture can be gabbroic or anorthositic texture depending on cooling. So gabbro is actually a mafic rock which is rich in Mg and Fe, whereas anorthosite is a leucocratic rock, that means light colored rock, maybe grayish or whitish, which is rich in feldspar but lacks the Mg and Fe uh, in those rocks. So okay, so depending on the type of magma and type of elements left in the magma, it will form gabbroic or anorthositic texture depending on cooling. Okay, so next in the scenario is, say we'll take a bulk composition of P. Okay, we can take a bulk composition of P, say which is of diopside 80 and anorthite 20. Okay, diopside 80 and anorthite 20, which is obviously pyroxene rich because diopside is 80%. It is similar to above just figure, and is then the case first diopside crystal will follow. It will be same thing here also. It will be same thing. It will touch this liquidus curve. Then R will be the first diopside crystal that will form. Then it will come to it will follow this line. It will come to eutectic point ultimately, and whenever it is as it is going down, it will continuously give diopside crystal. Remember, it will give only pure diopside crystal it will give, and then it will come here, and then the first anorthite crystal will start form, and then the liquid will give both a diopside and anorthite simultaneously at this point. So for temperature corresponding to P and bulk composition X bulk, we have only liquid phase. F equals to 2 minus 1 plus 1, that is 2. For both 2 T and X are variable. So both T and X are variable. So if you think that if you're thinking that how we are taking F equals to C minus P plus 1 and not C minus P plus 2, so actually we have a derivation of this. So depending on the Tx curve, this is actually a Tx curve, not a Pt curve, remember. So because of this Tx curve, and we are keeping our pressure as a constant. Okay, so this is an isobaric diagram, right? So because of that, we get this as plus 1, okay, and not plus 2, which was there in our PT diagram in water, having only one component, that is H2O. Okay, so apart these things apart, at point Q and F equals to 1, so at line we get F equals to 1. First crystal of pure diopside appears as liquid starts cooling. Line intersects as R. Okay, so this is the first crystal as just we have discussed. So continuous reaction, liquid 1 will give diopside plus liquid 2. So since liquid 2 is more anorthite rich than liquid 1, as T decreases, more and more diopside crystals and total solid solution follows path RV, and liquids evolve along QI. So here RV, this will follow the crystallization path is RV, whereas the melting path will be Q to I. Now the discontinuous reaction, a reaction on which I is discontinuous. At point I, the anorthite start crystallizing along with diopside. Liquid will give diopside anorthite. The same thing that happened in the first case. Total soil solution, soil composition follows VW path again. At point I, F equals to 0 at that yeah, eutectic point. System has no independent variables, so it's an invariant point that can change the system, and system is stuck at invariant point I. After liquid is consumed, phi equals to 2, F equals to 1. Now temperature below the solidus, now temperature can cool down the solid along WY line. So WY line, it is follow WY line, it will follow. After reaching the eutectic, it will come here and then it will follow here. So the liquid path is PQI, whereas solid path is RVWI. So liquid path is PQI and solid path is RVWY, like that. So resulting rock texture, dominant mineral, diopside, pyroxene, euhedral to subhedral crystal. Remember, I have taught you euhedral means all the sides are very prominent without any angularity in between them. So it will be euhedral crystals are sharp edged crystals. Okay, subhedral means little bit of roundness can be expected from crystals. So it will form euhedral to subhedral crystals. Texture is coarse grain. Coarse grain means very big grains you will have, possibly granular or poikilytic texture. Possibly granular texture or poikilytic texture. I'll show it to you how these textures look like. If slowly cooled, then only you will get granular or poikilytic texture and coarse grained. Anorthite sparse interstitial plagioclase. We will have very interstitial plagioclase. Okay, small plagioclase over big large plagioclases. Small plagioclase will go in the void space and interstitial spaces. Small plagioclase. Okay, so our overall texture will be rock is typically pyroxenite, which will be high. Pyroxenite is a rock which contains a lot of pyroxene. Okay, pyroxenite. So with equigranular diopside, equigranular or euhedral dioxide. Equigranular, equigranular is also the name of granular texture. Granular texture can be said as equigranular too. Okay, so granular texture and equigranular texture are same. So I'll show it to you how these two textures will look like. We will, don't worry, we will talk about texture in details in later classes, but I'll just try to show you so that you can remember all these things. Again, I'll draw this microscopic view. I'll draw two textures, granular texture, and if you are drawing this, you can also draw this crosshair in your exam paper. Yeah, like this. Try to draw as much diagrams as possible in your exam paper. That will fetch you good marks. So equigranular texture look like this, of sharp grains. So equigranular, as the name suggests, the grain size will be more or less equal to one another. This is the equigranular texture, and these are actually all diopsides, pyroxenes. These are actually diopsides or pyroxenes. Okay. If you are drawing this in the say um, in your answer sheet, definitely try to write it if this figure is in CPL or in XPL. I've drawn this as CPL diagram, so you will write it as CPL, or sorry, not CPL. This is actually will be PPL, plain polarized light. Or else if I have drawn this in CPL, I have to draw all the cleavages present. Remember, pyroxene have 90-degree cleavages, so we'll have to draw cleavages as well, so that will be very hectic. So better to draw it in PPL, because we are trying to show the texture only here. Okay, we're trying to show the texture, so try to draw equigranular crystals, and this will be diopside crystals, and this is an equigranular texture, or we can also say equigranular, or can be just granular texture. Both can be said. Same thing. Next is a poikilotic texture. A poikilotic texture will be like this, where there will be a single lath of say feldspar, and in between you will find some crystals of diopside. This is a diopside. This is a plagioclase or feldspar. It can be the opposite also. It can be a say if a pyroxene, and inside there will be a lot of laths of say if I'm drawing is here only. So this is a big pyroxene crystal. You will find laths of feldspar like this. This is also an poikilotic texture, where there will be a host mineral, big host mineral. This is the host. This is the host mineral, whereas this is the included minerals. The smaller crystals of one mineral is enclosed in larger crystal of another mineral, that is called a poikilotic texture, whereas equal sized grains containing the rock is called a equigranular or a granular texture. Hope you understood. And next will be, these are the dominating textures, dominant minerals texture, anorthite, and overall texture. This will be the resulting texture. And say we have the summary of the textural difference between scenario 1 and scenario 2. So features: scenario 1 will have anorthite if it is more than diopside, and scenario 2 is where diopside is more than anorthite. So here dominant mineral will be anorthite, here will be diopside. First crystallization will be anorthite, and then there will be diopside. Texture will be intergranular, subophitic. Here it will be granular, poikilotic. Rock type will be gabbro and orthositic gabbro. Here it will be pyroxenite, because a lot of pyroxene will be there. Here it will be minor phase, interstitial or enclosing diapside. Here it will be interstitial anorthite. Okay. So now fractional crystallization. So during crystallization, anorthite An begins to crystallize first, whereas liquid will give L2 plus anorthite. So now we will talk about fractional crystallization, where we will be taking out the crystal or the melt, and then we will carry out the reaction. So on left side of the equation there is no anorthite. In the left hand side there is no anorthite. So even if we keep removing anorthite, it won't impact the process, and the path will follow BDI. So even if we take out the anorthite, will follow the path B, D, and I. So same thing will happen because it is giving anorthite, we are taking anorthite out. So again, it will giving anorthite and we are taking anorthite out. So since there is no anorthite in the left hand side of the reaction, that is in liquid is giving a liquid too, but anorthite, even if we take out anorthite, so nothing will happen. The liquid will remain same. Okay. So that is the reason why it will follow the same path. Therefore, fractional crystallization FC does not impact the system significantly. So fractional crystallization will not impact the system significantly. Now next is melting of diapside anorthite system. So pure anorthite melts at 1553 degrees Celsius and pure diapside melts at 1391 degrees Celsius. These are very important temperature. You can, if you want, you can write this in your answers while drawing the diagram. So a mixture of diapside and anorthite melts at 1274 degrees Celsius. Okay. When heating, a mixture contains, say, so we are now doing melting. We doing the opposite. We are now melting diapside and anorthite system. So let's say we are taking a rock of composition anorthite 80% and diapside 20%. So at 1274, that is the eutectic point, the first melt will form with the eutectic composition of 40% anorthite and 60% diapside. Here at this point, the first melt will form having diapside of say 60% and anorthite of 40%. Since we are taking, remember we are taking a composition of rock where the anorthite percentage is 80%, but the first melt that will form will be of composition which will be richer in diapside. And here all the diapside will be melted and the reaction will follow this path. So at 1274, the first melt will form, which is a composition 40% anorthite and 60% diapside. Despite the bulk composition being 20% diapside, the bulk composition will have been 20% diapside, but we are getting melt having composition of 60% diapside and 40% anorthite. The initial melt has 60% diapside, indicating rapid depletion of diapside. So as more diapside will be getting out from a less diapside rich rock, so it will be depleted out very fast. So once diapside is depleted, once diapside is completely melted, only liquid plus anorthite will remain. So only liquid which is rich in anorthitic composition and anorthite crystals will remain with the composition where F equals to 1. It will follow that line of liquidus. So F equals to 1 implies movement along the BI line where all anorthite will melt at point B corresponding to the initial bulk composition of 80% anorthite. The same thing will happen as we just progress from up topward to downward. It will be going from after all the diapside is finished, it will follow this curve where it will be following this BD line, or the BD line. Last melt that will form will be of melt B, and then last crystal that will be melted will be of composition B and C respectively, melt and the crystal, and then it will go upward towards A. So F equals to 1 implies movement along the line BI, where an anorthite will melt at point B corresponding to the initial bulk composition of 80% anorthite. Okay. So this is the equilibrium melting of diapside anorthite where there is no fractionation. Now we will talk about fractional melting of, let's say, 75% anorthite and 25% diapside. So now we are just changing the composition a little bit. Say 75% anorthite and 25% diapside. At the eutectic point, phi equals to, we know that this phi equals to all three phases, so degree of freedom will be 0, invariant point. So once dioxide is depleted, also the melt is continuously removed from only A and will remain. So again, the same thing will happen. It will first touch the eutectic point, and then since dioxide is less, more dioxide will be melted at eutectic point, and it completely after completely melting dioxide, it will be remaining with liquid and some anorthite. So once the dioxide is depleted and also the melt is continuously removed from, then only the anorthite will remain, and it will jump the curve to 1553. Since we are removing the melt continuously, so at eutectic point this will happen at once dioxide is depleted and also the melt is continuously removed, because this is fractional melting, right? So we are always taking out the melt after the reaction is finished. So the melt is continuously removed, then only anorthite will remain, and it will jump the curve to 1553. That is the pure anorthite melting temperature, 1553 Celsius, without following the IB curve. So it will, after dioxide is finished, it will directly jump to here, 1553 degrees Celsius of pure anorthite at the liquidus curve. It won't follow the path, jump the curve without following the IB curve. It won't follow the path. So that is up to, that is the eutectic system discussion up to this point.